volt. To derive two group equation for a critical homogeneous reactor, we start by writing the homogeneous energy dependent diffusion equation and splitting the scattering term into two parts. For mathematical simplicity, we shall ignore the presence of delayed neutrons. Then you have the steady state form as minus d del square phi plus sigma phi is equal to integration 0 to EC sigma subscript s e dash to e phi d dash plus integration EC to E0 sigma s e dash to e phi e d dash plus xi p integration 0 to E0 gamma sigma f phi d dash, where E0 is the upper energy, that is 10 mega electron volt. So we have to define the first neutron flux phi 1, which is a function of position vector r, as phi 1 is equal to integration EC to E0 phi d, and the thermal neutron flux can be written as phi 2 is equal to 0 to EC phi d. So your all fission neutrons are born with energies lying in the first group. So your xi1 may be written as integration EC to E0 xi p d is equal to 0, and xi p can be written as integration 0 to EC xi p d is equal to 0. So by integrating your expression over first energy group for 0 to EC, you have your expression minus del square integration 0 to EC d phi d plus integration 0 to EC sigma phi d. This will become integration 0 to EC d integration 0 to EC sigma s phi d dash plus integration 0 to EC d integration 0 to EC to E0 es phi d dash. So the last term drops out, and there is no upscattering of neutrons out of the thermal group. So we have integration 0 to EC sigma s d is equal to sigma s, where E dash is greater or equal to 0 and smaller or equal to EC. So your first term will reduce to integration 0 to EC d dash integration 0 to EC sigma s phi d, which is nothing but integration 0 to EC sigma s phi d dash. Now putting the value of your minus del square integration 0 to EC d phi d plus integration 0 to EC sigma phi d, you can have minus d2 del square phi 2 plus sigma a2 phi 2 is equal to g1 to phi 1, which is a function of position vector, where your sigma a2 is equal to sigma 2 minus sigma s2, and your sigma 2 is equal to 1 by phi 2 integration 0 to EC sigma phi d. This is the average total cross section for the thermal group, and we can write sigma s2 is equal to 1 by phi 2 integration 0 to EC sigma s phi d, and it is the average scattering cross section for thermal neutrons. Now your d2 is equal to 1 by phi 2 integration 0 to EC d phi d as the average diffusion coefficient for the thermal group, and g12 is equal to 1 by phi 1 integration 0 to EC d integration EC to E0 sigma s phi d dash as the average transfer cross section for neutrons going from first into the thermal group. Then let us discuss the fast neutron. For fast neutrons, let us integrate from energy EC to E0. So the first term in the right hand side will drop out since there is no upscattering. Now the equation will become minus d1 del square phi sigma r1 phi 1 is equal to gamma 1 sigma f1 phi 1 plus gamma 2 sigma f2 phi 2, where your sigma r1 is equal to sigma 1 minus sigma s1 is equal to sigma a1 plus g12 is the removal cross section for fast neutrons. It is defined as the sum of absorption cross section and the cross section characterizing removal of fast neutrons due to downscattering into the thermal group. We can also refer it as slowing down cross section. It is very much different from absorption cross section. So your gamma 1 sigma f1 is equal to 1 by phi 1 integration EC to E0 gamma sigma f your phi d dash, and your gamma 2 sigma f2 is equal to 1 by phi 2 integration 0 to EC gamma sigma f phi d dash, where sigma 1, sigma s1 and d1 are defined by equations with the limits of integration from EC to E0. So we have now two group diffusion equation, and the source term in the first group is due to fission neutron only, and in the thermal group it is due to neutrons slowing down from the first group. So what will happen in a Bayer reactor? For a Bayer reactor, we assume that all the extrapolated boundary for the first and the thermal neutron group is same. That is your phi 1, which is a function of R0 vector, is equal to phi 2, which is a function of R0 vector, and it is nothing but 0, where your R vector is equal to R0 vector defines the extrapolated boundary of the assembly. In a large reactor, both fast and thermal neutron fluxes have almost the same shape and differ only in their magnitude, and they are characterized by the same spatial dependence. Therefore, by assigning the same value to the geometrical buckling, we have your del square plus bg square phi 1, which is a function of r, is equal to 0, and your del square bg square phi 2 is equal to 0, where phi 1 and phi 2 satisfy the boundary condition given by the equation. Now the two group diffusion equation can be arranged as d1 capital D1 bg square plus sigma capital R1 minus sigma gamma 1 sigma f1 whole multiplied by phi 1, which is a function of position vector, is equal to sigma 2 sigma f2 gamma 2 phi 2 is equal to 0. So minus g12 phi 1 plus d2 bg square sigma a2 phi 2 is equal to 0. Okay. So now discuss the two group critically condition for a Bayer homogeneous reactor. For a non-trivial solution of the simultaneous equations, the condition is that the determinant of the coefficient of phi 1 and phi 2 must be 0 as per Cramer's rule. So we can write determinant of d1 bg square plus sigma r1 minus gamma 1 sigma f1 minus gamma 2 sigma f2 minus g12 d2 bg square sigma a2 is equal to 0. So you can have d1 bg square plus sigma r1 minus gamma 1 sigma f1 whole multiplied by d2 bg square plus sigma a2 minus g12 sigma 2 gamma 2 sigma f2 is equal to 0. Now we can define diffusion length characterizing the fast and thermal neutron as L1 is equal to d1 by sigma r1 minus gamma 1 sigma f1 root over, and your L2 is equal to root over of d2 sigma a2. In terms of L1 and L2, you can simplify the resultant expression, and you can write gamma 2 sigma f2 by sigma a2 whole multiplied by g12 by sigma r1 minus gamma 1 sigma f1 whole multiplied by 1 plus L1 square bg square multiplied by 1 plus L2 square bg square is equal to 0. And the two group critically condition for a Bayer homogeneous reactor is expressed like this. So we can very well relate this to 6-factor critically condition formula. So we have to realize that the quantity 1 plus L1 square bg square and 1 plus L2 square bg square signify the non-leakage probabilities for fast and thermal neutrons respectively. Now your capital P subscript small f is equal to 1 by 1 plus L1 square bg square, and your Pt is equal to 1 by 1 plus L2 square bg square. So the fast factor can be written as the product of two terms, that is gamma 2 sigma f2 by sigma a2 is equal to gamma 2 sigma f2 by sigma AF subscript F superscript subscript A superscript F whole multiplied by sigma subscript A superscript F by sigma A2 is equal to eta F. Where eta is the average number of neutrons produced in fission per neutron absorbed in the fuel, and F is the thermal utilization factor. Similarly, we can write the second bracketed term as G12 is equal to G12 divided by sigma R1 minus gamma 1 sigma F1 is equal to G12 by sigma R1 multiplied by sigma R1 by sigma R1 minus gamma 1 sigma F1. For an infinite medium, the rate at which first neutrons are removed is given by sigma R1 phi 1 R, and the rate at which first neutrons are slowed down to thermal group is G12 phi 1, which is a function of R. Hence, the ratio G12 by sigma R1 gives the probability that a neutron is not absorbed in group 1, since most of the absorption in the first region occurs in resonance. This ratio may be identified as the resonance escape probability P. So P can be written as G1 square by sigma R1. So your first fission factor epsilon is defined as the ratio of the total number of neutrons produced in fission to the number produced by thermal neutrons induced fission. So your epsilon is equal to gamma 1 sigma F1 phi 1 plus gamma 2 sigma F2 phi 2 by gamma 2 sigma F2 phi 2. For eliminating phi 1 from the above expression, from the this expression with Bg square is equal to 0, we have phi 1 is equal to gamma 2 sigma F2 phi 2 whole divided by sigma R1 minus gamma 1 sigma F1. Now your first fission factor epsilon is equal to sigma R1 by sigma R1 minus gamma 1 sigma F1. So the right hand side can be identified as a product of resonance escape probability and first fission factor. So your G12 by sigma R1 minus gamma 1 sigma F1 is equal to P epsilon. So the sixth factor critical condition for two group theory is eta F P epsilon P F P T is equal to 0. For a reactor in steady operation, the power level depends on the position of the control rods inside the reactor. It is therefore useful to rewrite the criticality condition in terms of absorption cross section of the medium for thermal neutron. So sigma A2 is equal to G12 gamma 2 sigma F2 by D1 Bg square plus sigma R1 minus gamma 1 sigma F1 subtracted or minus D2 Bg square. Okay. So two group equation are coupled differential equation. To decouple this expression, we have to express phi 1 in terms of phi 2. So your phi 1 will be minus D2 del square plus sigma A2 phi 2 by G12. So a fourth order differential equation can be obtained for phi 2, which is nothing but del square phi 2 minus sigma R1 minus gamma 1 sigma F1 by D1 plus sigma A2 by D2 whole multiplied by del square phi 2 minus G12 gamma 2 sigma F2 by D1 D2 phi 2 is equal to 0. Now your delta to the power 4 phi 2 minus 1 by L1 square plus 1 by L2 square del square phi 2 minus k infinite minus 1 by L1 square L2 square phi 2 is equal to 0, where k infinite is the infinite medium multiplication factor, which is nothing but eta F P epsilon. Now if we eliminate phi 2 instead of phi 1, we can write the equation satisfied by phi 1 as well as phi 2. So your del to the power 4 phi minus 1 by L1 square plus 1 by L2 square del square phi minus k infinite minus 1 L1 square L2 square phi is equal to 0. To solve the equation, we have to assume that the extrapolated boundaries for both fast and thermal neutron fluxes are same. So your phi 1 is equal to phi 2 is equal to 0. And this can be characterized by the same spatial dependence. So we can obtain a quadratic equation in B square, that is B to the power 4 plus 1 by L1 square plus 1 by L2 square multiplied by B square minus k infinite minus 1 L1 square L2 square is equal to 0. So the two solutions of this equation are mu1 square is equal to 1 by 2 L1 square L2 square multiplied by minus L1 square plus L2 square plus root over of L1 square plus L2 square whole square plus 4 multiplied by k infinite minus 1 L1 square L2 square. And your minus mu2 square is equal to 1 by 2 L1 square L2 square whole multiplied by L1 square plus L2 square plus root over of L1 square plus L2 square whole square plus 4 multiplied by k infinite minus 1 L1 square L2 square. Since k infinite should be greater than 1 for the critical reactor, both mu1 square and mu2 square will be positive, so that mu1 and mu2 are real. So you have your del square plus mu1 square x1 is equal to 0 and del square minus mu2 square x2 is equal to 0. So this equation will depend on the geometry of the system. And the permissible expression for x1 and x2 for infinite slab, a sphere and an infinite cylinder is like this. So for infinite slab, x1 is equal to cos mu1x and x2 is equal to cos hyperbolic mu2x. For a sphere, x1 is equal to sin mu1 r by r and your x2 is equal to sin hyperbolic mu2 r by r. And for infinite cylinder, your x1 is equal to j0, which is a function of mu1 r, and x2 is equal to I0, which is a function of mu2r. So the general solution will be a linear combination of x1 and x2. And you can write phi1 is equal to a1 x1 plus c1 x2. Similarly, phi2 is equal to a2 x1 plus c2 x2. So out of these four constants, a1, a2, c1, c2, only two are independent because phi1 and phi2 are interdependent. So by choosing a2 and c2 as independent, we can write phi2 is equal to s1 a1 x1 plus s2 c1 x2. So your s1 s2 are coupling coefficients. So these are given by s1 is equal to d1 by d2 multiplied by 1 by L1 square all multiplied by 1 by L2 square plus mu1 square to the power minus 1. And the s2 is equal to d1 by d2 1 by L1 square 1 minus L2 square minus mu2 square to the power minus 1. So a1 and c1 can be determined by using the source condition and the boundary condition for the case of interest. Okay. So any doubt? So next we shall discuss the critical equation. Thank you.